Our solar system's king, the colossal planet Jupiter, holds a secret, a truly astonishing secret about its distant past. Recent scientific discoveries emerging in early 2025 have peeled back layers of time. They reveal a Jupiter that was once far grander than the giant we know today. Imagine a version of this magnificent gas planet that was not just larger, but staggeringly so, dominating its cosmic surroundings with an even greater presence. This isn't an idea from the pages of science fiction, some fantastical creation of an imaginative author. Instead, it's the compelling conclusion drawn from meticulous research and careful analysis of celestial mechanics. Planetary scientists have uncovered evidence suggesting Jupiter was once twice its current diameter, a truly breathtaking thought. This finding dramatically reshapes our view of its early history and its role in the solar system's formation. The sheer scale of this ancient Jupiter is difficult to comprehend fully. A diameter double its present size means it would have occupied a much larger volume of space, a veritable behemoth compared to its already impressive modern form. But its physical size wasn't the only dramatically different aspect of this primordial giant. Its magnetic field, that immense invisible force field generated deep within the planet and extending millions of kilometers into space, is believed to have been an incredible 50 times stronger than it is now. These remarkable details were recently published in the prestigious scientific journal, sending ripples of excitement through the astronomical community. This paints a vivid picture of Jupiter in its youth, a truly dominant, supercharged entity in the nascent solar system, its influence stretching far and wide across the cosmic neighborhood in which our Earth would eventually form and life would take hold. This period of Jupiter's gigantism occurred very early in the solar system's timeline, a crucial phase in its development. Scientists estimate this phase was around 3.8 million years after the very first solid materials, the building blocks of planets, began to coalesce from the protoplanetary disk surrounding our young sun. This is a mere blink of an eye in cosmic terms, placing this supersized Jupiter in an era when the solar system was still a chaotic, formative environment, far from the relatively ordered system we observe today. Young planets were still migrating, their orbits shifting and evolving. Vast amounts of gas, dust, and rocky debris filled the interplanetary spaces, remnants of the system's birth. Understanding Jupiter's immense size and power during this critical epoch is therefore vital for our cosmic understanding. It provides key context for piecing together the complex puzzle of how all planets, including our own precious home, came to be. This groundbreaking revelation, brought to light in 2025, is far more than just an interesting astronomical fact to be filed away. It fundamentally alters our understanding of Jupiter's entire life story, its planetary biography. It suggests a significantly more turbulent and energetic youth for the gas giant than previously conceived by most planetary models. The pioneering work by planetary scientists Konstantin Batygin of Caltech and Fred C. Adams of the University of Michigan has provided this new, profound insight into our solar system's largest planet. Their research effectively opens a new observational window, a way to look back. This window allows us to peer back into the early, formative, and often violent days of our solar system's creation, reminding us that planets are not static objects, but dynamic worlds, with rich, evolving histories that continue to unfold over eons. So how did scientists manage to uncover this extraordinary secret from Jupiter's deep past, a past hidden for billions of years? The answer lies not in direct observation of this ancient Jupiter, which is impossible, but in the subtle movements of some of its smallest companions. The researchers focused their attention on two of Jupiter's small inner moons, Amalthea and Thebe. These are not the famous large Galilean moons like Io or Europa, which are worlds in their own right. Amalthea and Thebe are much smaller, irregular bodies orbiting relatively close to the giant planet. It turns out that their current orbits hold the key, acting as faint echoes of past conditions. These tiny worlds have served as unwitting historical recorders, their paths through space carefully sculpted by Jupiter's gravitational influence over vast timescales, preserving clues to its former self. Amalthea and Thebe exhibit unusual characteristics in their orbits. Specifically, their orbital planes are slightly tilted or inclined relative to Jupiter's equatorial plane. This slight tilt has been a point of curiosity for astronomers for some time. Why weren't their orbits perfectly aligned, as one might expect for moons formed in a disk around the planet or captured into equatorial orbits? The answer, it seems, lay hidden in Jupiter's dramatic past transformation. The scientists, Batygin and Adams, employed powerful computer simulations to investigate this mystery. These sophisticated simulations can model the complex gravitational interactions within planetary systems. Crucially, they ran these models backwards in time, a kind of cosmic archaeology, to reconstruct the conditions that must have existed in the early solar system to produce the orbits we see today. The results from these intricate simulations revealed something truly extraordinary and enlightening. The present-day orbital tilts of Amalthea and Thebe could be precisely explained, but only under a specific set of past circumstances. These conditions required that Jupiter was once substantially larger in diameter and possessed a significantly more powerful magnetic field than it does at present. As this initially bloated proto-Jupiter gradually cooled and contracted over millions of years, its gravitational influence on its inner moons subtly changed. Its powerful magnetic field also weakened as its internal dynamics altered. This period of planetary shrinkage and magnetic field decay carefully sculpted the final orbital configurations of Amalthea and Thebe, locking them into their present, slightly inclined paths as a lasting testament to Jupiter's grander youth. These small moons, Amalthea and Thebe, are relatively unassuming celestial bodies when compared to their giant planetary host. Amalthea, the third moon from Jupiter, is an irregularly shaped reddish object, likely a captured asteroid or a remnant planetesimal. Thebe, the fourth known moon, is similarly irregular and orbits just beyond Amalthea. Yet despite their modest sizes, they have provided monumental clues to understanding Jupiter's evolution. Their subtle orbital characteristics, these slight deviations from perfect alignment, are like delicate fingerprints. They are fingerprints left behind by a younger, more dominant and physically larger Jupiter. This remarkable piece of scientific detective work beautifully demonstrates how even the smallest members of a celestial family can help us unlock the grand secrets of planetary evolution and the history of our solar system. This remarkable discovery about Jupiter's significantly larger past self aligns beautifully with our current leading theories concerning the formation of gas giant planets. These colossal worlds, like Jupiter and Saturn in our own solar system, do not simply spring into existence in their current, relatively stable forms. Their formation is a dynamic and lengthy process. It is generally understood that they begin with the accumulation of a solid core, composed of rock and ice, which then grows massive enough to gravitationally accrete vast quantities of gas, primarily hydrogen and helium, from the surrounding protoplanetary disk. This initial phase of rapid gas accretion results in the young planet becoming extraordinarily puffed up. It is initially very hot, diffuse, and somewhat chaotically structured, a far cry from the more ordered giant we see today. Imagine this newly formed Jupiter, a truly enormous entity, far exceeding its current impressive dimensions. It would have glowed with the intense heat generated by its formation process, the conversion of gravitational potential energy into thermal energy as material rained down onto its core and envelope. This bloated, incandescent state, however, is a temporary phase in the life of a gas giant, albeit one that can last for millions of years. Over these vast cosmic timescales, a gradual but persistent process of cooling takes place. The planet radiates its immense internal heat out into the cold vacuum of space. As it cools, it also inevitably contracts. The relentless inward pull of its own gravity compresses the gas, causing the planet to shrink in size and become significantly denser. This cooling and contraction is a natural, expected part of a gas giant's long-term evolution. The new findings regarding Jupiter's past size, indicating it was once twice its current diameter, provide strong observational support for this theoretical model of gas giant formation and evolution. The estimated timeline also fits neatly into this picture. The period of 3.8 million years after the formation of the first solids in the solar system is sufficiently early for Jupiter to have still been in this significantly expanded, puffed-up phase, before the long process of cooling and contraction had substantially reduced its girth. This suggests that Jupiter's contraction phase was a very significant period in its history, a time during which its changing gravitational field had a profound influence on the orbits of its nearby inner moons like Amalthea and Thebe. The discovery of a much stronger magnetic field also corroborates this scenario. A larger, hotter, and more vigorously convecting interior in young Jupiter would naturally generate a more powerful dynamo effect, leading to the vastly stronger magnetic field described. Therefore, the Jupiter we observe in the night sky today is a more mature, settled version of its former self. It has largely completed its primary phase of contraction and has cooled considerably from the fiery heat of its youth. However, the evidence of its more boisterous and expansive past has not been entirely erased. It remains, subtly etched into the orbital architecture of its inner moons, a lasting legacy of its grander beginnings. This enhanced understanding provides a more complete and dynamic biography for Jupiter. It is not merely a static, unchanging ball of gas that has always been as it is now. Instead, it is a dynamic celestial object with a fascinating and transformative history. This transformation from a larger, hotter, and more magnetically active body to its current state is a key element in understanding its present characteristics and its overall role in the solar system. What are the broader implications of this ancient, much larger Jupiter for our understanding of the solar system as a whole? Its influence during that early formative epoch would have been truly immense, far exceeding what previous models might have suggested. A more massive and physically larger Jupiter, existing so early in the solar system's history, would have exerted a significantly stronger gravitational pull on everything around it. This could have profoundly affected the formation pathways and subsequent migration histories of the other planets, including the terrestrial planets like Earth. It might have played a crucial role in scattering smaller planetesimals, potentially delivering water and organic materials to the inner solar system, or conversely, preventing other large planets from forming in certain regions. It could even help explain some of the current, somewhat puzzling architectural features of our solar system, essentially meaning parts of solar system formation models may need rewriting. This new startling knowledge about Jupiter's early gigantism is part of a much larger ongoing trend in planetary science. Our understanding of the solar system, and indeed the cosmos, is in a constant state of evolution and refinement. Very often, as our observational tools become more powerful and our theoretical models more sophisticated, we find that our initial simpler ideas about celestial bodies were incomplete or even incorrect. Consider the planet Mercury, for example. For a long time, it was widely believed that Mercury was tidally locked with the Sun, always presenting the same hemisphere to our star, much like our Moon does with Earth. However, radar observations in the 1960s revealed this was not the case. We now know it possesses a 3-to-2 spin-orbit resonance, meaning it rotates 3 times on its axis for every 2 orbits it completes around the Sun, a more complex and dynamic relationship than first assumed. Then there is the fascinating story of Pluto. Once classified as the 9th planet, it was later reclassified as a dwarf planet. For decades, it was often depicted in textbooks and popular imagination as a simple, inert, frozen rock at the frigid edge of the solar system. But the breathtaking images and data returned by NASA's New Horizons mission in 2015 completely overturned this simplistic view. Pluto was revealed to be a surprisingly active and diverse world. It boasts vast glaciers of nitrogen ice, towering mountains made of water ice, a tenuous but complex atmosphere, and even strong evidence suggesting the presence of a subsurface liquid water ocean. Similarly, the distant ice giants, Uranus and Neptune, were once considered relatively bland and featureless balls of gas. Modern observations, however, have shown they possess dynamic atmospheres with colossal storms, incredibly complex and lopsided magnetic fields, and internal conditions that might even allow for the formation of diamond rain deep within their interiors. Our view of these remote worlds has become far richer and more wondrous. Each new discovery, such as this revelation of Jupiter's colossal youth, adds another crucial piece to our ever-expanding cosmic puzzle. It serves as a powerful reminder that the universe is perpetually full of surprises and that our current understanding is always a work in progress. What we think we know with certainty today might well be revised, expanded, or even overturned by the discoveries of tomorrow. Science is not a static collection of facts, but a dynamic process of continuous learning, questioning, and refinement. The story of Jupiter's ancient supersized past is another compelling chapter in this ongoing human journey of cosmic exploration. It highlights the wonderfully dynamic nature of celestial bodies and underscores the profound importance of looking ever more closely at the universe, always questioning our assumptions, and embracing the inherent complexity and beauty of the cosmos. Our quest for understanding is and always will be never truly over.